Chapter 9, Matrices, Section 9.2, Matrices and Matrix Algebra. In the next two sections, we'll study matrices and see their application to solving systems of linear equations of the type that we looked at in Chapter 8. So first of all, matrix is a rectangular array of numbers, usually enclosed in brackets. The plural of matrix is matrices. Some examples of matrices are shown. You see that matrix A has 4 elements, or we call them entries, 4, 2, 0, and 1, 2 rows and 2 columns. Matrix B is a single row. It would be considered to have 3 columns and 3 entries. Matrix C would be thought of as having 3 rows and 2 columns, 6 entries altogether. A matrix of m rows and n columns is said to be of order m by n. That's read m by n, not m times n, by the way. If m equals n, that is, if the number of rows equals the number of columns, then the matrix is said to be square of order m. So a square matrix of order 3 would be a matrix with 3 rows and 3 columns. Example 1 says, determine the order of matrices A, B, and C above, and identify any square matrices. So let's begin with matrix A. A is a square matrix. So we'd say A is square of order 2. Or we could say that it has order 2 by 2. We'd say B has order 1 by 3 because it has 1 row and 3 columns, each column consisting of just a single entry. So we always list rows first, followed by columns. And C has order 3 by 2, having 3 rows and 2 columns. So A is the only one of the 3 that is considered to be a square matrix. A square matrix is easy to identify because it looks like a square, basically, with numbers inside. The elements, which are usually numbers, within a matrix are called entries. The entry of row I and column J of matrix A would be denoted with the lowercase a and then ij as a subscript. So the first number in the subscript would be the row position, and the second number would be the column position. In example 2, we're asked to refer to matrices A, B, and C again above and identify the specified entry. Alright, I've scrolled back up so we can actually see matrices A, B, and C. A12 would be the entry in matrix A in row 1 and column 2. That would be the 2. So we'd say A12 equals 2. A21 would be the entry in row 2, column 1. That would be the 0. So we'd say A21 equals 0. B13 would be the entry in matrix B in row 1, column 3. Row 1, column 3 would be the position of the entry 2. C22 would be the entry in matrix C in row 2 and column 2. That entry would appear to be 4, so C22 is equal to 4. Next, we define matrix equality. 2 matrices A and B are said to be equal, and we write A equals B if, first of all, they have the same order, the same number of rows and columns, that is, and secondly, their corresponding entries are equal. So matrices that are equal must have the same order, the same number of rows and columns. Example 3 asks us to identify the values of A, B, and C such that 2 matrices are equal. Notice that both matrices have order 2 by 3, 2 rows and 3 columns. So that condition is satisfied. The second condition that must be satisfied is that corresponding entries must be equal. So what that would tell us, first of all, is that entry A should be the same as entry 0 in the first row, second column. So that would tell us, of course, A itself must be 0. Next thing we see is the entry 1 would have to correspond to the entry B minus 1 in the second matrix. So we would have to have 1 equal to B minus 1. From that it follows that B would have to equal 2. And finally, the entry in row 2 column 3 of the first matrix must equal the corresponding entry in the second matrix. That would be 6. So it follows that 2C would have to equal 6. From that equation it follows that C would have to equal 3. Basic operations on matrices include addition, subtraction, scalar multiplication, and matrix multiplication. So we actually define two different types of multiplication. Multiplication by a scalar, and we'll define a scalar in a few minutes, and multiplication of matrices, two matrices themselves. First of all, matrix addition. If two matrices have the same order, their sum is found by adding their corresponding entries. If two matrices have different order, their sum is undefined. So what this is telling us is that we can only add matrices that have the same order, the same number of rows and the same number of columns. If they have different order, they cannot be added. When we add them, we simply add the corresponding entries to find the sum of the two matrices. On the next page we see the definition of matrix subtraction, very similar to that of matrix addition. If two matrices have the same order, their difference is found by subtracting their corresponding entries. If two matrices have different order, their difference is undefined. So rather than adding, we're subtracting. Otherwise, the definitions are basically the same. Example 4 says, given the matrices as defined below, find, if possible, A plus B, A minus B, and A plus C. So let's begin with A plus B. We notice that both A and B are of order 3 by 2. That is, they have 3 rows and 2 columns, so their sum is defined. Their sum will also be a 3 by 2 matrix and will be found by adding corresponding entries of A and B. So for example, we would add 0 and 2. Those would be considered to be corresponding. 5 and 0. That would be 5 plus 0. And so on. 5 plus 2. 2 plus negative 2. Negative 1 plus 4. And 4 plus 0. And then adding, we get 2, 5, 7, 0, 3, and 4. Very simple, very easy. A minus B. Only difference here is we'll subtract corresponding entries. So for our first entry in row 1, column 1, it would be 0 minus 2. In row 1, column 2, 5 minus 0. Then 5 minus 2. Two minus minus 2. Minus 1 minus 4. And 4 minus 0. Subtracting, we would obtain negative 2, 5, 3, 4, -5, and 4. What about A plus C? Well, A is a 3 by 2 matrix, but C is a 2 by 3 matrix. It has 2 rows and 3 columns. So although they have the same number of entries, they both have 6 entries, their orders are different. So there's no way to correspond entries. Therefore, the sum of A and C is undefined. And that's all we can say about that. So A plus C is undefined. Matrix addition is commutative. That is, if A and B have the same order, then A plus B equals B plus A. We can see from how matrix addition is defined that this is a very reasonable thing to assume. A real number that's used in computations with matrices, but that is not itself an entry of a matrix, is called a scalar. So if you're working with a number that sort of sits outside of the matrix, is not associated with the matrix itself, then that number is referred to as a scalar. This then leads to the definition of an operation called scalar multiplication. Let A be a matrix and let C be a scalar. Then the scalar multiple of A by C is denoted, that's just read C times A, and is found by multiplying each entry of A by C. So scalar multiplication is performed simply by multiplying each entry of the given matrix by whatever the scalar is. And we can perform a scalar multiplication on any matrix of any order. We can also use scalar multiplication to define the additive inverse or opposite of a matrix. The additive inverse of a matrix A is denoted minus A and is defined as follows. Minus A is the scalar multiple of -1 and A, -1 times A. Moving on to example 5, given matrices A and B as defined in example 4, find 2 times A, minus A, and A plus 3B. I've gone ahead and written the 2 matrices in question from example 4 so that we can easily refer to them. And we begin with 2A. This is a scalar multiple of 2 times the matrix A, and basically all we do is we take each entry of A and multiply it by 2. Pretty much how you would expect it to work. And then we just compute the products. So 0, 10, 10, 4, -2, and 8. Minus A. Well, minus A would just be like multiplying each entry in matrix A by -1. That is, just take the opposite of every entry in matrix A. So that would be 0, -5, -5 again, -2, +1, and -4. Notice that the opposite of A does not necessarily mean that all of the entries of A are negative. You could have 0, you could have positive entries. It depends on the sign of the entries in matrix A. Finally, A plus 3B would be the entries of matrix A plus 3 times the entries of matrix B. That would be 6, 0, 6, -6, 12, and 0. Being almost out of time, I paused the video and just added corresponding entries to come up with the final result. We'll continue with this section in the next video.